welcome back. Today we are diving into Performance Optimization 7.1, Importance of Performance Optimization. Performance optimization is a fundamental aspect of modern software development, especially in the realm of back-end systems. In today's digital landscape, where users demand fast and responsive web applications, optimizing performance has become more critical than ever. This section delves into the significance of performance optimization in back-end development and explores its impact on user experience, business outcomes, and overall system efficiency. Enhanced user experience. One of the primary reasons why performance optimization is crucial is its direct impact on user experience. Studies have shown that users have little patience for slow-loading websites and applications, with research indicating that a mere 1-second delay in page load time can result in decreased user satisfaction, increased bounce rates, and lower conversion rates. Conversely, improving performance by reducing page load times, minimizing latency, and enhancing responsiveness can lead to higher user engagement, increased retention, and improved customer satisfaction. By optimizing back-end systems, developers can ensure that users have a seamless and enjoyable experience, resulting in greater brand loyalty and positive word-of-mouth recommendations. Improved business outcomes. Performance optimization also has significant implications for business outcomes and bottom-line results. In today's competitive market landscape, where digital experiences play a crucial role in customer acquisition and retention, the performance of web applications can directly impact key business metrics, such as revenue, conversion rates, and customer lifetime value. Faster loading websites and applications tend to attract more visitors, drive higher engagement levels, and ultimately lead to increased sales and revenue generation. Moreover, improved performance can enhance brand reputation, strengthen customer trust, and differentiate a company from its competitors, ultimately contributing to long-term business success and sustainability. Optimal resource utilization. Efficient resource utilization is another critical aspect of performance optimization. Inefficiently designed back-end systems can consume excessive computing resources, such as CPU, memory, and network bandwidth, leading to scalability issues, increased infrastructure costs, and diminished system reliability. By optimizing performance, developers can streamline resource usage, reduce operational expenses, and maximize the scalability and reliability of back-end systems. Moreover, optimizing performance can enable organizations to accommodate growing user traffic and workload demands without the need for significant infrastructure investments or capacity upgrades, thus ensuring optimal resource allocation and cost-effectiveness. Competitive advantage. In today's digital economy, where user expectations are constantly evolving, performance optimization can provide organizations with a competitive advantage. Websites and applications that deliver superior performance and responsiveness are more likely to attract and retain users, outperform competitors, and establish themselves as industry leaders. Conversely, organizations that neglect performance optimization risk falling behind their competitors, losing market share, and damaging their brand reputation. By prioritizing performance optimization as a strategic imperative, organizations can stay ahead of the curve, adapt to changing market dynamics, and capitalize on emerging opportunities in the digital marketplace. Overall system efficiency. Performance optimization also contributes to the overall efficiency and stability of back-end systems. Well-optimized back-end systems are more resilient to traffic spikes, resource constraints, and unpredictable workload patterns, ensuring consistent performance and availability under varying conditions. Additionally, optimized systems are easier to manage, troubleshoot, and maintain, reducing the likelihood of performance-related issues, downtime, and service disruptions. By investing in performance optimization initiatives, organizations can enhance the efficiency, reliability, and maintainability of their back-end infrastructure, enabling them to deliver reliable and high-performing digital experiences to their users. 7.2 Identifying Performance Bottlenecks. Performance bottlenecks are obstacles that impede the smooth operation and optimal performance of back-end systems, leading to slower response times, degraded user experience, and decreased system efficiency. Identifying and addressing these bottlenecks is crucial for optimizing the performance of back-end applications and ensuring they meet the expectations of users and stakeholders. This section explores the concept of performance bottlenecks, common sources of bottlenecks in backend systems, and strategies for effectively identifying and mitigating them. What is performance bottlenecks? Performance bottlenecks can manifest in various forms and arise from different areas within a backend system. Generally, a bottleneck occurs when a particular component or resource becomes a limiting factor that prevents the system from performing at its maximum capacity.
Common types of performance bottlenecks include CPU bound, occurs when the CPU becomes overwhelmed by processing tasks and cannot keep up with the workload demand, resulting in delays in task execution and overall system slowdown. Memory bound, arises when the system's memory resources are exhausted or inefficiently utilized, leading to excessive memory consumption, swapping, or fragmentation, which can degrade performance and cause instability. Disk I/O bound, occurs when disk input-output operations become a bottleneck, typically due to slow disk read-write speeds, high disk utilization, or inefficient data access patterns, resulting in delays in data retrieval and storage. Network bound, arises when network bandwidth or latency becomes a limiting factor, causing delays in data transmission, communication, or resource access between components or systems. Database bound, occurs when database operations such as queries, inserts, or updates become a bottleneck due to inefficient query execution, poor indexing, database contention, or excessive resource utilization. Identifying performance bottlenecks requires a systematic approach and a combination of monitoring, profiling, and diagnostic techniques to pinpoint areas of concern and determine their root causes. Performance monitoring, implementing robust monitoring solutions to collect and analyze key performance metrics such as CPU usage, memory usage, disk I/O rates, network throughput, and database performance indicators. Profiling and profilers, using profiling tools to analyze the execution behavior and resource utilization of backend applications and components. Load testing and stress testing, conducting load tests and stress tests to simulate realistic workload conditions and assess the system's performance under varying levels of user traffic, concurrency, and data volume. Code reviews and code analysis, performing code reviews and static code analysis to identify potential performance issues, such as inefficient algorithms, suboptimal data structures, excessive resource allocation, or unnecessary computation. System profilers and tracers, using system profilers and tracers to capture detailed system-level information, such as function call stacks, system calls, thread activity, and process interactions. Once performance bottlenecks have been identified, the next step is to implement targeted solutions and optimizations to alleviate them and improve system performance. Code optimization, refactoring and optimizing code to improve efficiency, reduce resource consumption, and eliminate performance bottlenecks. Resource allocation and scaling, scaling resources such as CPU, memory, disk, or network bandwidth to accommodate increased workload demands and alleviate performance bottlenecks. Caching and data storage optimization, implementing caching mechanisms to cache frequently accessed data, queries, or computations in memory or distributed caches to reduce latency and improve response times. Network optimization, optimizing network configurations, protocols, and communication patterns to minimize latency, reduce network congestion, and improve data transfer rates. Database optimization, optimizing database configurations, schema design, and query performance to improve database throughput, reduce query execution times, and minimize database contention. Caching is a fundamental technique used in back-end development to improve application performance by storing frequently accessed data, resources, or computation results in temporary storage for quick retrieval. Client-side caching. Client-side caching involves storing cached data or resources directly on the client-side device, such as a web browser or mobile app, to reduce the need for repeated requests to the server and improve application performance. Browser caching. Web browsers can cache static assets such as HTML, CSS, JavaScript files, images, and multimedia content to reduce the need for repeated downloads and speed up page load times. Local storage. HTML5 introduced the Web Storage API, including local storage and session storage, which allows developers to store key-value pairs of data locally on the client-side device. Service workers. Service workers are JavaScript scripts that run in the background of web browsers and intercept network requests, allowing developers to implement custom caching and offline capabilities for web applications.
Server-side caching involves caching data, content, or computation results on the server-side infrastructure to reduce database load, minimize processing overhead, and improve response times for subsequent requests. In-memory caching. In-memory caching stores cached data or objects in memory, RAM, rather than disk storage, allowing for fast access and low latency. Popular in-memory caching solutions, such as Redis and Memcached, provide key-value stores with support for data expiration, eviction policies, and distributed caching, enabling high-performance caching for web applications. Content Delivery Networks, CDNs. CDNs are distributed networks of servers located in multiple geographic locations worldwide, designed to cache and deliver static assets, such as images, videos, style sheets, and scripts, to end users from the nearest edge server. By caching content closer to end users, CDNs reduce latency, improve content delivery speeds, and offload origin server traffic, enhancing the scalability and performance of web applications. Database caching. Database caching involves caching query results, database objects, or frequently accessed data in memory or disk storage to reduce database load and improve query performance. Database caching solutions, such as query caches, result caches, or object caches, store recently accessed data in memory or a separate caching layer, reducing the need for repeated database queries and speeding up data retrieval for subsequent requests. While caching can significantly improve application performance and scalability, it also introduces various considerations and challenges that developers must address. Cache invalidation. Ensuring cached data remains up-to-date and consistent with the underlying data source is crucial to prevent stale or outdated cache entries. Developers must implement cache invalidation strategies, such as time-based expiration, event-driven invalidation, or manual cache clearing, to maintain cache integrity and consistency. Cache coherency. Maintaining cache coherency across distributed cache nodes or layers is essential to ensure consistent data access and avoid cache inconsistency issues. Developers must consider cache synchronization, cache replication, and cache coherence protocols to synchronize cache updates and maintain data consistency in distributed caching environments. Cache size and eviction policies. Managing cache size and eviction policies is critical to optimize cache performance and resource utilization. Developers must choose appropriate cache eviction algorithms, such as LRU, least recently used, or LFU, least frequently used, to evict stale or least valuable cache entries and make room for new data, ensuring optimal cache utilization and performance. Cache security. Securing cache data and preventing unauthorized access or tampering is essential to protect sensitive information and maintain data privacy. Developers must implement cache security measures such as encryption, access control, and data masking to safeguard cache data from security threats and unauthorized access. Load balancing and scalability are critical aspects of backend development that play a vital role in ensuring the performance, reliability, and availability of web applications, especially in high-traffic environments. Importance of load balancing and scalability. In today's digital landscape, where web applications serve millions of users concurrently, ensuring optimal performance and availability is paramount for businesses to meet customer expectations and maintain competitive advantage. Improve performance and response times. Load balancing distributes incoming requests across multiple backend servers, preventing any single server from becoming overwhelmed and ensuring that each request is processed efficiently. By distributing the workload evenly, load balancers reduce response times, minimize latency, and improve the overall performance of web applications, providing users with a seamless and responsive experience. High availability and fault tolerance. Load balancers play a crucial role in achieving high availability and fault tolerance by detecting and mitigating server failures, network issues, or performance bottlenecks in real time. By automatically rerouting traffic to healthy servers, load balancers ensure uninterrupted service availability, mitigate downtime, and enhance the reliability of web applications, even in the event of server failures or disruptions. Scalability and elasticity. Scalability is the ability of a system to handle increasing workload or user demand without sacrificing performance or reliability. Load balancers facilitate horizontal scaling by distributing incoming traffic across a scalable pool of backend servers, allowing web applications to scale out dynamically to accommodate growing user demand or traffic spikes. Load balancing can be implemented using various techniques and algorithms, each with its own strengths, considerations, and trade-offs. Round robin. The round-robin algorithm distributes incoming requests evenly across a pool of back-end servers in a circular manner, ensuring each server receives an equal share of the workload. While simple and easy to implement, round-robin load balancing may not consider server health or capacity, leading to uneven distribution under certain conditions. Least connection. The least connection algorithm routes incoming requests to the server with the fewest active connections, ensuring that new requests are directed to the least loaded server. This approach optimizes resource utilization and minimizes response times by distributing the workload based on server capacity and availability. Weighted round robin. The weighted round robin algorithm assigns a weight to each backend server based on its capacity, performance, or priority, allowing administrators to control the distribution of traffic according to specific criteria. By adjusting server weights dynamically, organizations can achieve more granular control over load distribution and prioritize critical workloads or applications. Least response time. The least response time algorithm routes incoming requests to the server with the fastest response time, minimizing latency and optimizing user experience. This approach dynamically measures server response times and adjusts traffic distribution to ensure optimal performance and responsiveness for end users. Scalability is essential for accommodating growing user demand, handling traffic spikes, and ensuring the long-term viability of web applications. Horizontal scaling. Horizontal scaling, also known as scaling out, involves adding more servers or instances to distribute the workload across multiple nodes. This approach enables organizations to increase capacity, improve fault tolerance, and handle growing user demand by scaling resources horizontally across commodity hardware or cloud instances. Vertical scaling. Vertical scaling, or scaling up, involves upgrading existing servers or hardware to handle increased workload or performance requirements. While vertical scaling offers simplicity and centralized management, it may have limitations in terms of scalability, cost-effectiveness, and hardware constraints compared to horizontal scaling. Cloud computing platforms such as Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, provide scalable infrastructure services, including compute, storage, and networking resources on demand. By leveraging cloud services, organizations can dynamically provision and scale resources based on demand, optimize cost efficiency, and improve agility and flexibility in deploying web applications. Microservices architecture. Microservices architecture decomposes monolithic applications into smaller, independently deployable services, each responsible for specific business functions or features. This modular approach enables organizations to scale individual components or services independently, optimize resource utilization, and improve fault isolation and resilience, facilitating horizontal scaling and agility in application development and deployment.